Okay, on behalf of the open committee, I'd like to welcome everyone to the first post-pandemic physics program. And I see a very good attendance from the first year graduate students. Welcome to Brown, and this is for you. And when the committee had our list of speakers, we want to have someone who is very distinctive. And then Professor David Nelson from Harvard is American, distinguished American physicist who was born in Germany, Stuttgart. David made many contributions to physics. He's a member of the National Academy of Science, and he has too many awards to mention. I will mention one, 2004 Oliver Bulkley Prize in Physics. And then today, when he showed up, he flew into our emeritus parking spot. I said, no, he should park in the Nogo laureate spot. And then we had Brown's permission, and then Professor Leon Tuber's permission to park David's car there. And the Nogo committee is having a meeting soon, in 2 weeks, when else will win. Good luck, David. David is connected to our own Professor Costellus, and he played a mic called me many times. David played a major role in the Nobel Prize work, Salas and Professor Costellus about for calculating the universal jump in the superfluid density across the KT transition in superfluid films. And Professor Nelson also played a major role in the 2D melting theory in the discovery of the hexatic phase with for Halperin. So his contribution is too long to read. From Wikipedia, you go ahead and read it there. And today he will tell us his latest work in mutilated surfaces. And then I'm looking forward with some anxiety here. Don't worry. Welcome.
Thank you. Well, it's a really great honor to be back at Brown and to be involved in the post-COVID colloquium. It's an honor for me. It's an honor for my automobile, which is now parking in Leon Cooper's place next to Mike Costellus's car. So my automobile is now going to be insufferable after this, but it's really a pleasure. And as I mentioned, I've been coming to Brown for a long time, and first time I came, I was a postdoc, and I was collaborating with another Brown professor, Leo Kadanoff. And he would come up to Boston and I would drive down, and that's when I first got to know a little bit about this wonderful university. And I remember one of our discussions, Leo was quite interested in these XY model things and putting on symmetry breaking perturbations. And I said, you know, Leo, there's this great paper by Costellus and Thales that, you know, we should go have a look at it. Let's go to the library. And it was back when we had libraries before the internet. And I was amazed to learn that Leo Kadanoff didn't know where the science library was. I mean, he could just figure things out. He didn't really need to go, but in fact, we found it, and we did look up Mike and David Thales' very, very beautiful paper. So I want to tell you a story today that has a little bit of ancient history associated with it. And I want to contrast linear polymer chains in a good solvent, which do a kind of self-avoiding walk in the solvent. This is a crude model of a, say, polyethylene oxide polymer with sheet polymers. And this is a simulation of a sheet polymer. It's a rather old one. But for me, still quite amazing thing that was figured out way back in the 1990s, sort of, was that these sheet polymers can have a spontaneously broken symmetry, even in 2 dimensions. And I think I have here something that I can illustrate the symmetry with. Hopefully this backpack won't fall on the floor. So here's an ordinary sheet of graph paper. Nothing on my hands or my sleeves. I don't have any sleeves really. And when you have thermal fluctuations in such an object, you might expect it to crumple. At high temperatures, there will be entropic reasons for this to happen, much like what happens to this polymer. And there's a kind of order parameter. It's a little bit like a spin that you can erect to describe this possible crumpling just by erecting a normal to every point in the surface. And if it's a little bit wrinkled, the normal is going to wobble around and so forth. And as you make this surface bigger and bigger, you can ask, is there long range order in the normal? And as Mike and others in the audience know, there's a theorem. It goes back to Merman and Wagner and Hohenberg that says it's impossible to have a continuous broken symmetry in 2 dimensions because thermal fluctuations are so powerful in destroying this delicate long-range order. But in fact, there's a way of avoiding the theorem for these 2D sheet polymers. You think of the normals as being like an order parameter. And there can be long-range order in a low-temperature flat phase. And if you want to read about this, you can look at this nice review by Bari and Sinai about how this system manages to avoid this prohibition against a long-range ordered phase in 2 dimensions. Even back in those times, we were quite interested in atomically thin sheets. And this is the so-called rag phase of molybdenum disulfide. And you can see that in this electron micrograph, I presume that's what it is, this is a polymeric, this is an analog of a sheet polymer, but with stiff covalent bonds. And you can see it's little, sort of looks like a crumpled piece of paper, but it's atomically thin. And we never really found out a good system to study back in those ancient times, but along came graphene. And this is a very beautiful paper by Paul McEwen and Melina Blies from Cornell University, where they actually made ribbons of graphene. You can sort of barely see the graphene ribbon here. It's 10 microns across. And what I'm going to show you, if I can make this movie run, is the result of using this refrigerator magnet to activate this magnetic pad at the end and sort of torture this atomically thin object. This atomically thin object has an aspect ratio of maybe 20,000 to 1. It's 20,000 times thinner than it is wide. And it's the analog of a single molecule biophysics experiment, basically, but done on graphene in water at room temperature. So it's subject to the thermal fluctuations. And this group has, tour de force of nanotechnology, also made atomically thin graphene springs. So this is an atomically thin graphene spring. And as you can see, when you pull on it, you laser cut these holes in it. This is called kirigami. It's a relative of origami. You fold, make beautiful swans and stuff by folding paper. With these holes, you pull on this thing, and it escapes into the 3rd dimension by twisting and turning. And it's atomically thin. And this has gotten a lot of us interested in this problem again, and trying to understand some combination of the mechanical and even electrical properties of these objects. And so with that introduction, I want to tell you about the statistical mechanics of mutilated sheets and shells. And let me also say at the very beginning, I know that Sean Ling and Mike Kosterlitz will not hesitate to interrupt me if there's something unclear. But I'd like to also welcome questions from the postdocs and grad students, especially the G1s. If something is not clear, it's probably my fault. And if you have that question, there'll be lots of people in this room. I can almost guarantee you they'll have the same question. They will be secretly happy that you stop. And of course, the faculty, all the faculty will be most welcome to interrupt. So anyway, here's an outline. I want to tell you something about the story of this statistical mechanics of very thin sheets with the motivation of having atomically thin sheets around. And you'll see that there's a nonlinear parameter, somewhat like the Reynolds number in fluid mechanics. How many of you have run into Reynolds numbers in your studies? Okay, so some people. It tells you the analog of what would be the fine structure constant in QED for this kind of physics. And it turns out that it goes like a Young's modulus, it's an elastic constant times the size of the ribbon or whatever it is squared divided by a bending rigidity. And it turns out to be enormous. The Young's modulus of this crumpled piece of paper is 10 to the 6th. And you know, if you can figure out the fractal dimension of this object when I crumple it, publish. It's not easy. It's a very non-trivial problem, even in classical physics. And you'll see that the result of this large Foeppl-von Karman number at finite temperature is strongly scale-dependent elastic constants. So elastic constants aren't constant. They actually depend on the size of the system in a highly non-trivial way. It's not just like a logarithm, logarithmic dependence on system size. It's something that's very strong and seems to have been observed experimentally. Then I'll talk about mutilation, the physics of puckers in these fluctuating finite temperature sheets. And these puckers, as you'll see, have kind of mechanical analogs of Ising spins. And in a system that we studied, they order antiferromagnetically on a fluctuating background of these flexural phonons that control the statistical mechanics of the thin plates. And if there's time at the end, I'll tell you a little bit about when you have a background curvature. So you have a fluctuating thin shell, atomically thin shell, maybe even atomically thin cylinder. So this is the recent stuff. It's on the archive. It was done with Abby Plummer, who herself is a graduate of Brown. And thank you for sending her our way. And a postdoc, Paul Hanakata, who did his graduate work at Boston University. And then the work on curve stuff started with Jason Pelosi, who was my student. He's now at the University of Oregon. And Andre Kashmurov, who is on the faculty at Princeton. So again, any questions so far? I made myself understandable. Okay, so here's a story. It goes back to 1904, and it leads to something called the Foeppl-von Karman equations. These were two very distinguished scientists working on the physics of thin sheets. And the idea is if you have a thin elastic sheet, of course, there are atoms and molecules that make it up. But one way to think about it when it's allowed to escape into the third dimension is to say there's some background flat sheet that's shown down here. That's this thing R0 that's parameterized as a function of x1 and x2. And then the phonons, the excitations are in-plane phonons, the usual in-plane phonons that you might encounter in the solid state physics course. And then there's these out-of-plane modes that allow it to go into the third dimension. And if you ask yourself, what happens to this little reference line segment on the reference sheet once it gets thermally excited, it typically gets longer, or maybe shorter, or whatever, when it gets a little bit crumpled by escaping into the third dimension, and courtesy of the in-plane phonons as well. And then you can work out what happens to the metric, basically, when this occurs, and it's described by a strain tensor. Standard thing in the elasticity theory, but here it's highly nonlinear. So the strain tensor that comes out of this little exercise has symmetrized derivatives of in-plane phonons, but it also has this strange nonlinear term that depends on the out-of-plane displacement F. So there's a bending energy shown here. There's a stretching energy that comes from the contractions of the strain tensor. This bending energy is very soft. It turns out rotational invariance means that the dependence has to be Laplacian of F squared. This kappa is another elastic constant called the bending rigidity. And then in 2 dimensions, mu is the shear modulus and mu plus lambda is the bulk modulus. So that's the problem here. And now the effect of this nonlinearity is what's going to cause some of the remarkable things that I'll tell you. But let's just do something very simple at first. Let's just say we take this as our energy and we try to minimize, given some boundary conditions, and find the configuration of the surface. So, if I crush this thing, I have some boundary conditions. What equations would I have to solve to understand this crumpled piece of paper? So you can do that in a variety of ways, but you're going to see that it's important that these flexural phonons, kind of a matrix vector potential that acts to displace these symmetrized derivatives here, it allows this very soft escape into the 3rd dimension. And if I now look at t equals 0, what you can do, this is kind of an analogy with electrostatics. You have a condition on the strain tensor. Don't worry about the details here, but because its divergence must be 0, you can write it as a 2 derivatives of an Airy stress function. These are anti-symmetric 2x2 matrices. This Airy stress function is an analog of the electrostatic potential, except this is a Laplacian squared elasticity theory. So it's a richer phenomenon than you might have encountered in electrostatics. And now if you just minimize as a function of this Airy stress function and the flexural phonons, you get these, at least in some circles, quite famous equations due to Foeppl-von Karman. They worked this out in 1904, as I said, and you can see if you want to figure out what happens with given boundary conditions, you've got 4 derivatives, Laplacian squared here and here. And then you have these nonlinearities on the right-hand side. The nonlinearity on the right-hand side here in F is actually the Gaussian curvature. And so if I have like a defect, it's like a point mass in a kind of baby version of general relativity. It was actually done 10 years before, and it's not the same. It involves extrinsic curvature as well as the intrinsic Gaussian curvature. So it's a different theory, but it has similar challenges. And we only have solutions in very special cases like this one here. And the nonlinearity can be encapsulated in terms of these prefactors of the Laplacian squared. Kappa, it turns out, for thin sheets is exceedingly tiny, as is 1 over the Young's modulus. Young's modulus is giant, but this is 1 over the reciprocal is very small. So I have small quantities multiplying the highest derivative of the problem. That's what happens in the Navier-Stokes equations, the limit of vanishing viscosity. And the analogous thing to a Reynolds number, here's the Reynolds number for those of you who know what it is, for a viscous fluid with viscosity nu and speed u and size L. Here's the quantity that you can scale out and show controls everything. It's this Foeppl-von Karman number. And if you put in Young's moduli for paper and bending rigidities, and you have an 8.5 by 11 piece of paper, this Foeppl-von Karman number, which measures the strength of these nonlinearities, is 1 million. For graphene, it's 10 to the 12. So that already makes graphene kind of interesting, in my view. And now you can ask what happens when you try to do finite temperature stuff, not 0 temperature stuff, do the statistical mechanics of this problem. And it's a challenging problem because it's so nonlinear, et cetera, but you can get rid of the in-plane phonons. And the reason, if I go back a little bit here, the reason is these in-plane phonons, if you just square them and stuff, they only occur quadratically. So by doing some Gaussian functional integrals, you can just get rid of those phonons and focus down on what happens for the remaining degrees of freedom. And so that's what I'm symbolically representing here. You sort of do a partition function, integrating over those in-plane phonons. This is the energy that I was talking about, this nonlinear energy. And when the dust settles with this little calculation, there's an effective free energy that still has these very soft out-of-plane phonon modes with the bending rigidity here. And then there's a transverse projection operator that actually makes the problem highly non-local, acting on these derivatives of the out-of-plane tilts. So these little gradients, you can think of them as being like tilts of the Heisenberg order parameter. This is what allows this thing, it turns out, to have long-range order. But the easiest thing to do is just to take this nonlinearity and do perturbation theory in the Young's modulus, because that's what makes the problem nonlinear. And that's something Luca Politi and I did a number of years ago. And you can calculate with some Feynman diagrams this renormalized bending rigidity. And it's one of these problems in condensed matter physics where you think you have a straightforward calculation and it blows up, explodes. And the way it explodes is quite interesting, I think. So the renormalized bending rigidity is a function of some external wave vector, is the bare value. Then you get something proportional to temperature. It's a kind of low temperature perturbation theory we're doing here. And when you evaluate this little Feynman diagram, it's the same as this one here, symbolically, you find a correction to the bending rigidity. And it looks a priori good because you get a ratio of kBt over the bending rigidity. That's dimensionless. It's typically like 1/50 in many systems. There's a 32 pi cubed in the denominator. That's great. But then there's an infrared divergence in this integral that produces, as a prefactor, the Foeppl-von Karman number, which even if this is small, could well be 1,000,000 or 10 to the 12th for graphene. So it's an explosion of positive renormalization of the bending rigidity. And you can check, it's an experiment that even I can do, that merely by putting in these wrinkles, this sheet becomes a lot stronger. I mean, look at this pathetic unwrinkled piece of graph paper. It can't even hold its own weight under gravity. But put a few wrinkles in there. Okay, think of these as proxies for thermal fluctuations. It becomes strong. And in fact, what Luca Politi and I did was to try to do a little more sophisticated version of this thing, where we summed up the most diverging diagrams at every order in perturbation theory. And if you do that, you get a self-consistent equation. You get a Dyson equation, fancy name for it, for this renormalized bending rigidity, where it occurs on the left-hand side, but also on the right-hand side in the denominator. And then you get a self-consistent equation that you solve for this renormalized bending rigidity as a function of wave vector. And by taking the wave vector close to zero, you're looking at longer and longer wavelength undulations. And what you find is not just a logarithmic singularity, it's a singularity where the bending rigidity goes like 1 over the wavelength. So it says that this elastic constant doesn't have a Q goes to 0 limit. Some of you might know about long time tails. Well, this is long time tails on steroids because you go to longer length scales and these elastic parameters diverge. And strongly, diverge very strongly. So the fancy way of doing this was first worked out by Joe Aronovitz and Tom Lubensky, and it's a recent paper on fancy techniques for doing this. But one very useful tool for solving this problem more systematically is the renormalization group, the same kind of thing that was used to understand, for example, by Mike, the Kostostalos transition. And as you go to longer and longer wavelengths, you're driven away from that Foeppl-von Karman fixed point, which is already quite non-trivial, to another fixed point, which can be handled by these, turns out, by these perturbative renormalization group methods. And this is a finite temperature fixed point. And the results, which are more important probably than the fancy math, is that if I have a square of size L by L, the bending rigidity isn't a constant at long wavelengths anymore. It depends on how many wrinkles are in there, basically a finite temperature. And it scales with the edge length like L over a thermal length that I'll tell you about to the eta power. And eta is a universal critical exponent that's about 0.82, somewhere between 0.82 and 0.85. It's quite big. And then the Young's modulus, which tells me how easy it is to pull on this thing. I have stored length in the form of wrinkles. It gets softer. And it gets softer in a scale-dependent way. So none of these elastic constants are actually constant. They depend on the size of the system, even though 300 years of science suggests that they are constant at long wavelengths. It's not true for this particular system. And the Young's modulus gets softer and softer. Here's its exponent. And the crucial thing that tells you is a kind of Ginsburg criterion that tells you when this is going to be important. The easiest way to get it is to go back here and ask, when is this correction going to be comparable to what it's correcting? And that gives you a length scale beyond which you better pay attention to these scale-dependent elastic constants. And here's its functional form, depends on temperature. So at zero temperature, you don't have to worry about this stuff. You might have to worry about quantum fluctuations, but you don't have to worry about these thermal undulations. And it turns out, as pointed out to me by Paul McEwen, if you put in numbers for room temperature graphene with its appropriate Young's modulus and its appropriate bend rigidity, this length is about 0.3 nanometers. So at room temperature, if you're larger than that, pretty small length, 3 angstroms, you better pay attention to these running coupling constants.
Nice question.
Please.
Right, you pre-crumpled that piece of paper.
I did.
Yeah, rather aggressively.
I did.
Yeah.
I did it again.
Yeah. No, that's actually scary. So we're not talking about pre-crumpling here, right? This is all occurring simply. You're raising the temperature. It self-crumples and gets.
That's right.
Okay.
That's right. So it's a kind of a kludge. It's not actually what's happening, but it turns out that the wrinkles that I have pre-crumpled in here can be thought of as a proxy for the thermal fluctuations, which are dynamic, moving around, etc. It's a great question. Okay. Thank you.
Follow up.
Please.
Question. So for actual paper, crumbled paper.
Yeah.
The reason you have those wrinkles is because of the plastic deformation that happened.
That is correct.
The microscopic scale, right?
That is correct.
So because there you can set it equal to 0, those crumbling goes away.
That is correct. So that's a very, thank you, Sean. That's a very important difference. There are plastic deformations. These are kind of a quenched random analog of the thermal fluctuations, which also can stiffen things. Another nice experiment that I'm extremely fond of doing is just to make this piece of paper into a fan, thus putting in with plastic deformations, undulations, but only with a special wavelength in a special direction. And so here I have it. Okay. Now it's still very soft this way, but it's very hard to bend this way. That's like, you may have in the back of your house a garden shed with a corrugated roof. That's what makes the roof strong, is those corrugations. And that's what's going on, but it's going on without any active intervention by you or the experimentalist in general. It's going on because of thermal effects. Other questions? This is great. Yes, please.
If you wanted to bend something
Yeah.
and it was crinkled, you might be better off squeezing it, bending it, then let it re-crinkle.
Yes.
Would you be saving any energy doing that? Would it be at least theoretic function?
Well, so you could. So if you did that with thermally, it probably not a lot of hysteresis, at least for idealized graphene that is a perfect crystal and so forth. But if you do this with paper or you do it with tinfoil, that produces lots of plastic flow. There probably is hysteresis, and people have studied the noise that crumpled paper or tinfoil makes as it relaxes, for example. So there probably is hysteresis as you buckle and sort of snap, crackle, and pop your way around in the face. Absolutely. But I'll be talking about this thermal thing, and I'll show you some experiments in a minute. Other questions? Yeah.
We know that from
elasticity that is having here only true when it's smooth deformation.
Well, you have smooth deformations. Yes, that's right.
Then people's history doing that.
So, okay, so it's true. This elastic theory assumes that there's smooth deformations. If you're too violent, you'll start rupturing the covalent bonds of the graphene. Or maybe there'll be some dislocations that are present already and you'll start moving them around. But if the fluctuations are gentle enough, the thermal, and there's a low temperature regime where we think you understand this pretty well, then you're okay. You're not going to be producing any defects. But that's an interesting subject in some.
So what if the conclusion you have the nature you cut off this length scale of lattice?
Yes.
Here at the end is the graphene say that the length is about like 0.3 millimeters square.
Right, but fortunately, the physics that leads to these strange results happens not at short wavelengths, it happens at long wavelengths. So it's an infrared divergence. It's like critical phenomena where the details drop out and only appear maybe in this thermal length and maybe in the performance. So that's how we can get away with not looking at microscopic details. Are quite interesting and important, and they're going to come later in this talk as well. But that's why we can get away with this. Other questions? Yeah.
There's something that smells like a semi-wavelength I see on high order corrections for your order parameter.
Yep. Yeah, and you know that nonlinear theory, if you look at it, because there's sort of two fields involved, the in-plane phonons and the out-plane flexural phonons, it evades what in filtering would be the Coleman theorem and so forth. So there are boson modes, there's no doubt about it, but because the bend rigidity gets renormalized so strongly as a function of length, those logarithmic divergences that you might be familiar with go away. Okay, so there's experiments that test some of this, but I want to say one other theoretical thing which has only become better understood in the very recent past. Graphene, three-dimensional graphite, or any typical solid-state system with covalent bonds, if you heat it, it's going to expand. Okay? Almost all materials do that, except rubber bands. You put a rubber band with a weight on it, put a hairdryer on it, it'll shrink. It shrinks for entropic reasons. And graphene's at least in flat 2D space, is a very stiff material. You might expect it to expand, but you can see that this thing has shrunken compared to the 8.5 by 11 sheet that I started with. And so you can work out the coefficient of thermal expansion. And here the shrinkage is illustrated with this blue wrinkled paper superimposed on a flat white piece of paper. And so in fact, this thing is supposed to shrink when heated. Now I've added an external stress. There's all sorts of fascinating nonlinear physics associated with stress-strain relations. This is a system, this flat phase with all the wrinkles, it's automatically at a critical point. It's like self-organized criticality, which used to be a fashionable thing 25, 30 years ago. But this is an example where it really happens. And so there are nonlinear stress-strain curves. But I'll just focus on this piece here. This is the shrinkage I was just telling you about. So the calculation of the shrinkage depends on the exponent eta, depends on the cutoff. This is the ultraviolet cutoff, capital lambda times L thermal, etc. And if you calculate the coefficient of thermal expansion, which is rusty on this is the definition. You see how the area changes as you increase temperature. Temperature only comes in through this prefactor here, kBT, and this thermal length. You'll discover something quite negative. And in fact, there's recent simulations. This is imagine a simulation of crystal graphene at high temperatures. I'm not showing the wiggles in time here, but this is what happens at low temperatures. This is molecular dynamics by Paul Hanakata. you find this, as you heat it, the projected area goes down, down, down. You take a derivative, you calculate the coefficient of thermal expansion. It's indeed a negative slope. And this dashed line is the theory with no adjustable parameters. So at least on a simulation level, we understand how this thing shrinks. The system, which itself is always at a critical point. The experiments at Cornell did something which is really cool. They used a cantilever experiment to measure the bending rigidity of graphene ribbons of varying length. And this is what they noticed. If you put in 10 micron width for this thing, 40,000 times wider than it is thin, you've reached the Moore's law limit of thinness with these freestanding graphene ribbons. You ain't gonna get anything thinner than that. Putting in the size and the bending rigidity, which is about 1.2 electron volts, comes from density functional theory, and so forth. This is the Foeppl-von Karman number that comes out, 10 to the 12th. And as I said, the L thermal is 2 angstroms, so at room temperature. So what happens? Well, talk about other things for the rest of this colloquium, but what they found by just looking, measuring the bending rigidity, by looking at how this weighted pad got deflected. Standard experiment actually done by Galileo. He did the first theory of cantilevers, but not for graphene at room temperature. And this curve, this dashed curve, is the expectation from zero temperature density functional theory as a function of length. And from the slope, you can read off the bending rigidity. And at zero temperature, we would expect it to be 1.2 electron volts. That's what the best ab initio quantum mechanical calculations tell us. But what they actually found was not 1.2 electron volts. They found 7 kiloelectron volts. They found a 4,000-fold enhancement at room temperature. And if you put in the numbers into this formula, which is what the theory would predict, it does come out to be about 4,000. And if you don't like a 4,000-fold enhancement, you want something bigger, take your width not to be 10 microns, take it to be 50 microns, and it'll be 10,000-fold. So it depends on the size of the system, which takes some getting used to if you're a conventionally trained mechanical engineer or a physicist. It takes a long time to get used to it. In any event, most of the rest of the talk, I'll be talking about other atomically thin sheets which might mimic metamaterials. So I don't know of any experiments, but we were inspired by this material tin oxide. And it has a subset of atoms, say they're the tins, that are a little bit bigger than the oxygens, and they tend to pop out into the third dimension as a result. So they play the role of kind of easing spins, easing degrees of freedom. They can pop up or pop down. And it turns out the prediction, at least at zero temperature, is that this forms a kind of antiferromagnetic state, where half of them are up and half of the large balls are up, half of the large balls are down. You can also have lead sulfide, and the prediction there by Paul Hanakata and collaborators is that the large balls all want to be on the same side. So that's the analog of a ferromagnet. So we thought we'd do a simulation and some theory trying to understand this a little bit better. So we made a simple lattice model with springs and so forth, and we put in large atoms. Say every other site will be a large atom with a longer rest length in the plane, but we allow it to buckle out of the plane, and we allow it to have free boundary conditions on the edge. Maybe it's periodic boundary conditions, but it can adjust its area. And so what Abby did was to study this thing, and you basically take this particular particle and you force its rest length to be a little bit bigger. So this is the control parameter delta that kind of describes the elastic frustration of trying to fit a large ball in a sea of small balls. And of course, there'll be many other balls as well. There's a local Foeppl-von Karman number that you can make by the change in the area produced by this little dilation. If delta is negative, I'll show you that in a minute, we call it a stitch. It's a kind of negative dilation where the bonds shorten. And this is a simulation of one isolated such impurity. There we go. And of course, it wants to pop out of the plane, but it's tethered. It can't go arbitrarily far, and it could have gone down or up. So it has a kind of plus minus symmetry. And if you put a lot of these in to a material, say a square lattice, in a checkerboard pattern, you'll get a mechanical analog of an Ising antiferro. So now the question is, what happens when we heat it up? Anything interesting happen when we mutilate this nice pristine lattice? This is negative bond shrinkage, negative dilation that produces a kind of saddle. And if you on many college campuses, you can see this in tacoed bicycle tires, because I presume what happens when it gets cold is these metal struts shorten more than the rim wants to shorten, and so it produces a saddle, and so you can have interacting tacos, if you like, which also seem to form an antiferromagnet. So we study this thing. And I'll define it more precisely in a minute. This is a staggered magnetization. Actually, look at the square, and it's a little easier to study. And this is an order parameter that's going to tell us what happens when we heat this thing up. And you can see at low temperatures, so this is temperature measured in units of the bending rigidity. Low temperatures makes an antiferromagnet with a few defects in it. And then the staggered magnetization, which is a standard order parameter for antiferromagnet, starts to go crashing down. And then at high temperatures, it's looks like some kind of Q code where you put it in your iPhone to learn something interesting about your restaurant's menu or whatever. Anyway, it goes from this low temperature to this high temperature phase. And they are a phase transition that occurs at about 0.2 kappa. And if you estimate for some of these materials, it's about 800 degrees Kelvin. So you could imagine doing a vacuum experiment. Couldn't do it in water, but now this antiferromagnetic order parameter is riding on a fluctuating background of flexural phonons. So it's not a simple compressible Ising model. It's more like a compressible Ising model on steroids, as I'll try to convince you. Okay, so this is roughly where we think the TC is. We think there's a T to the 1 minus alpha singularity, for those of you who remember the ancient days for critical exponents, where alpha is a specific heat exponent. So, please. Yeah, of course.
Yeah, so if this two-dimensional film is an amorphous material, does it make it a spin glass?
Oh, if it were amorphous, there's all sorts of interesting spin glass issues. And even if it's just a triangular lattice of these puckers, for example, there's geometrical frustration. The geometrical frustration that you might well remember. So if I have a triangular lattice, now this is buckled up, then this wants to buckle down, then this one is getting confusing mixed signals. And so even on the level of a triangular lattice, there can be frustration. And if you have randomly located puckers, there could indeed be non-trivial spin glass stuff. So we stayed away from it just because we wanted to do something that was a little more amenable to our understanding. But that would be a fascinating thing. Thank you. Other questions? Yeah.
So because it's not spin, so it's not just up and down, it's
Yeah.
so it is the fish multiplying and the.
Well, thank you. So if I understand the question, it's not as simple as having up down only. There can be twists, there can be tilt, and so forth. As far as we can tell, we put in perturbatively those corrections. They don't change the long wavelength physics. So we can escape again, because there's long wavelength stuff not only going on with the flexural phonons, but also going on with the diverging correlation length of an Ising antiferromagnet. So this is a system which has two things that are simultaneously critical. The flexural phonons are automatically critical all the time in the flat phase, And then we have this Ising stuff on top.
But when you can see the visual.
Yeah, we can see it, but it doesn't seem to be very big, but it's allowed in the simulations for sure, absolutely. Okay, so when we understand this, I won't spend a lot of time on this part, is to introduce this staggered macroscopic magnetization. This is the standard trick for Ising antiferromagnets. Basically flip the sign of every other spin. These, of course, aren't spins, they're puckers that go up or down. And this is the local magnetization variable that takes something which is highly corrugated and sort of makes it more slowly varying. And should make this little change in variables. It's like you have a checkerboard pattern. You flip all the black squares and make them red, and then it would become uniform. So that's just a mathematical change of variables. But now, I apologize for this slightly busy slide, but it's things you've already seen, but then coupled together. So this is the flexural phonons, just what I was talking about earlier. Right, that describes the flexural phonons. And this is this nonlinear strain matrix. This is what you probably might have encountered in a graduate stat mech course. This is a Landau theory for an Ising antiferromagnet with a staggered order parameter. This is the thing that changes sign at TC in 2 dimensions. So we have this set of critical degrees of freedom, it's always critical. This set, which becomes critical when the mass goes away, the quadratic term in the Landau expansion. And then the most interesting part, in my view, is this coupling between the 2 degrees of freedom. And it's a compressional coupling that says that when you have a staggered Ising order parameter, that's going to couple to the dilation, local dilation of this strain matrix. And it turns out that this compressible Ising model on steroids, which is what I like to call it, distinguish it from the compressible Ising models that were studied before we allowed escape into the 3rd dimension. You can study lots of interesting things, but one of the most interesting for us is the thermal expansion. Remember that thing was always negative? This is the area divided by some reference area. It's dropping as a function of temperature here. At the transition, it stops, it doesn't drop anymore, it goes up. And that's the effect, we believe, of this coupling, constant G that I had in the previous slide here. And it says that when there's antiferromagnetic order, the packing in a sense becomes more efficient. And when you lose it, the thing swells because it doesn't pack well. In fact, you can see it in this little cartoon of bowling pins. The bowling pins pack very well when they're ordered antiferromagnetically in bonds. But if I start jumbling them up at random, it's got to swell. And that's what we think is going on. And you can work out the area change. This is the shrinkage that we talked about earlier, present even in an unmutilated film. This is the result of that new coupling. And it causes this thing to go up. In fact, it causes the slope, it turns out, to diverge. So you get a diverging thermal expansion coefficient. In fact, it's a specific heat-like divergence at the transition. It's a pretty strong one. It's stronger than logarithmic anyway. So instead of having a negative, you can control the coefficient of thermal expansion just a little bit like, if you go above the freezing point of water, there's a place where the thermal expansion coefficient vanishes. Okay, well, here it goes to infinity. And this is just more math. You can integrate out the infinite phonons, you find a long range interaction between the staggered magnetizations. But for us, the more important one is this one here, which turns out couples the Gaussian curvature of the fluctuating surface to the staggered magnetization squared via this logarithmic interaction. We think that puts the system in a different universality class than good old Armsucker Ising model. We're not sure of that, but if you do a simple renormalization group calculation for this W thing, it grows. It couples them more and more strongly at longer and longer wavelengths. And here's our best data with many different system sizes. It goes up to 192 maybe or something like that. Susceptibility, specific heat, and those of you who dimly remember, as I dimly remembered old days of critical phenomena, you can do finite size scaling. Bottom line is we get these exponents, alpha over nu, gamma over nu. This one's pretty close to Onsager, but this one is 4 standard deviations away. So we think it's likely there's a different universality class. If anybody can calculate this exactly, some conformal field theorists perhaps, please tell me. Okay, so I want to, in the remaining 5 minutes or so, maybe 10, tell you one more thing. So far, I've been working with flat sheets, things with no background curvature. But I could have equally well worked with some giant bucky tube with a very large radius, because I want to take a thermodynamic limit, or a large amorphous, maybe it has to be amorphous, perhaps, thin, atomically thin sheet, a shell, a thin shell. And I want to try to convince you, I won't talk about cylinders, I want to convince you though that this is different than that. The background, it knows about the background curvature. So what is the physics of thin fluctuating shells, maybe cylinders in the future? And I want to try to convince you that there's a Nogo theorem that says even if there's not a pressure difference between the inside and the outside of the spherical shell, you cannot make it bigger than a certain size. Otherwise, it will be collapsed by thermal fluctuations. No analog for here. For a flat sheet, no problem. But you cannot put on the spherical constraint. If it gets too big, it's going to crush itself, even with a non-zero pressure difference. So here is conventional crushing. I love to show this movie from Germany. For some reason, the Germans seem to like to do this sort of thing. Don't try this at home. So what was done? They took this. See if I can. Okay, they took this innocent railroad car, and it had liquid in it, and they drained all the liquid out. And they pumped it out, and of course, when they pumped it out, there's essentially zero pressure on the inside and atmospheric pressure on the outside. Goodbye, railroad car. So be careful with those railroad cars. I know you have them in Providence. So how would we do? How would we understand the atomically thin analog of this experiment? I won't go through the detailed math, but if you have a spherical background, you can make what's called a shallow shell approximation, or do a shallow shell theory, and work out the strain matrix. And it's the same kind of problem that we've just been talking about. No mutilation unless you're a railroad car here. And here's the normal nonlinear strain tensor. And here's the one that arises when you do this for a sphere of radius r. And notice it's linear in f, so it can tell, as you might guess, inside from outside. Positive f is not the same as negative f. And the radius of the sphere enters as a kind of coupling constant. So we have size-dependent coupling constants sort of in the game here. And I won't go through the details except to say that you get new terms beyond the nonlinear one that I was talking about. It has those eta exponents and some things that you can treat. You can treat it with the normalization group. You can treat it with perturbation theory. Here I've added a pressure. And to make a long story short and conclude the colloquium, I'll just tell you that if you work this out at finite temperatures, there's another dimensionless parameter that comes in. It's the square root of the Foeppl-von Karman number times kdt over kappa. And this is a dimensionless pressure. But even if you take the pressure at 0, when you get above a certain size, like 160 in these dimensionless units, the thing will be unstable and be forced to crush. So same thing we believe would apply to a hemisphere. which sort of by definition has the same pressure inside and outside, so pressure difference is 0. Someone tries to sell you a graphene parachute, don't buy it, don't even invest in it, because if it gets larger than a certain length, which is about 160 nanometers for graphene, it will crush itself merely by the act of closing into a hemisphere. So there you go. Don't buy that. At least don't buy it if it's bigger than 160 nanometers. You could say, oh, graphene is the strongest material, it's the thinnest material, blah, blah, blah. Just be careful when you invest. So with that, I will stop and thank you for your attention. Happy to answer questions, any more questions.
All right, thank you very much. That's a beautiful talk. Okay.
What's the one-dimensional analog? Imagine you're stuck in one dimension, you fluctuate out of that one dimension.
Yeah, okay, thank you. So I understand the question. I can have a polymer with very stiff directional dependent bonds to try to make it straight, but there'll be little fluctuations like this. And in one dimension, we know there's always a persistence length. So if, in fact, you might know better than I that the persistence length of this thing is something like the bending rigidity associated with bends like that divided by kb2. So at any finite temperature, if you go long enough, it's going to start bending, and it doesn't have the analog of the flat phase for us to talk about in the thermodynamic limit.
What happens if you don't apply attention?
You apply attention, just as for the sheet. You can iron out the wrinkles, and you can study that. And we haven't done linear polymers, so you can put force. Just like single molecule biophysics. It could be DNA, for example. Then there'll be fluctuations out of plane, but because there's a tension, they're non-zero. They shrink it, but they're not as violent as the ones I was talking about. But it's fun to look at this, and we actually get a kind of polymer-like analog of what happens to a very long ribbon. Its persistence length is about 5 kilometers. This graphene, but you can make it a little shorter and start asking those questions. I see as a question also. Right, that's right.
So thermal fluctuation can be thought of as a random force. Now, if you apply a regular or periodic force on this two-dimensional system, what does it affect the mechanical law?
Okay, so yeah, thank you. So to repeat the question, the thermal fluctuations are random and chaotic. It's kind of white noise in space and time. You put on something periodic, one thing you could get is this fan structure. And then it becomes highly anisotropic. And there's an anisotropic version of this physics that people like John Toner and Leo Radzichowski study. So it's anisotropic. Yes, please.
This is more of a math question, but if I'm, I deform away from the two-dimensional embedded plane into three-dimensional, if I do another theory definition and work in a complex coordinate system, then I can think about chirality. Is there any connection with that?
I don't know. It's possible with the negative dilation stitches that there's some chirality associated with those saddles.
Local chirality.
Yeah, local. And maybe chiral symmetry, but the short answer is I don't know.
In the beginning, you mentioned that in two dimensions it's impossible because there's a theorem which goes it's impossible to get the
right.
Is this the same reason why the diffusion equation in two dimension does not allow for long range correlation?
I don't know. I think there are logarithms in both systems. There are logarithmic singularities, infrared singularities, but here it's a much more powerful thing because the singularities scale as the linear dimensions of the system squared, not as the logarithm. So it's similar, but much stronger.
You talked a lot about negative thermal expansion
Yeah.
in the context of two-dimensional things.
Yeah.
But it also shows up in a lot of three-dimensional materials where it's not necessarily so well understood. So I'm wondering if you know, or if maybe you can speculate if entropic effects or kind of floppy sort of effects is that root.
Yeah, okay, so, okay, thank you. So for the analog of the things I've been talking about in 2 dimensions, to happen in 3 dimensions, I need it to be embedded in 4. So that's not likely to happen, but you're right, there are lots of materials that have negative coefficients of thermal expansion, and the usual picture, maybe no, is that you have some 3-dimensional meshwork, like a gel or something. And this is a model of a rubber band. Imagine this is the 3 dimension, maybe it's random, and so forth. You heat it up, there's an entropic shrinkage across these polymers, these floppy polymers, and that also causes a shrinkage. And for us, what was surprising to see it in a solid state physics system with stiff covalent bonds.
I was referring to systems with like maybe almost ionic solids, like scandium trifluoride.
Okay. Yeah.
Would you perhaps look for some soft mode or something like this?
Or a displacive phase transition, perhaps. So where you change the unit cell shape, you might get something like that there. I haven't checked carefully. That's an interesting question.
So you were talking about curvature at the end. Maybe I just missed this, but I noticed that you were integrating to find the curve exponents. You were integrating in 2-dimensional space. So when you go to curvature, are you now integrating in 3-dimensional space, or are you still integrating in 2D space, but you're not putting in this extra?
Okay, thank you. So when we have a curved background, we're integrating out the in-plane phonons again. We're doing it in a local tangent plane. And so there's a local tangent plane everywhere, but the plane itself is tilting around as it needs to reflect the spherical background state.
Okay, with that, let's declare victory, right? Overcome it, and then Professor Nelson's talk definitely give us confidence that we are going to be back to normal.
But Professor Nelson is putting back on his mask.
Let's thank Professor Nelson for a beautiful talk.